Hey y'all, in this video lesson, I'm going to be showing you a few fundamental trig identities. Before we get started, I want to encourage you to maybe have like a sheet of paper or a note card where you keep track of all these identities as we use them, and then make a habit of just going through and studying those and being very familiar with them, because as we use identities to prove stuff later on, you're going to need these in your vault to use to help you solve problems. I have a couple identities listed here that you might either highlight or put on that sheet of paper or note card that you're keeping track of. These are identities that you're probably familiar with, but I'm just kind of rewriting them here so that they're right there and available as we work through these problems. We have the quotient identity, which is tangent of theta equals sine over cosine, and then we have our reciprocal identities. So depending on the problem, you can kind of use these to help manipulate equations to prove things. So the first example, it says use the identities above to prove that tangent theta equals sine theta times secant theta. The first thing you want to do with these is see if you can convert any of these using the quotient identities or reciprocal identities. I usually you kind of want to work with one side first, one or the other. Sometimes you can work with both. You kind of just have to play around with it. And as you play around with it more, you're going to start to see what's going to be the quickest way to go about something. There's not necessarily one way to solve it. There can be, you might see a different way than what I see, but we still end up with the same answer, and that's okay. As long as you get to the end of the problem and it's proven, then you're good. So I've got secant theta on the right side here that stands out to me. And I know that secant theta is 1 over cosine theta. So I can swap those out and use some algebra, because where I'm going with this is you kind of have to know where you're going so that you know where to start, basically. But what I'm seeing is tangent theta is sine over cosine, and secant theta is 1 over cosine. So it's like, it's pretty close there. So let's use that. I'm just going to play with the right side here. I have tangent theta equals sine theta, and then secant theta is 1 over cosine theta. Now you might see where I'm going here. This is a real quick example. I can put sine theta over 1. You don't have to, but you can. And then we're just multiplying fractions. Tangent theta, sine theta times 1 is sine theta. 1 times cosine theta is cosine theta. That should look familiar. If we go scroll up to the quotient identity, tangent theta is sine theta over cosine theta. I'm going to take this one step further just to tidy it up and end up with a statement that is undoubtedly true. I can substitute sine theta over cosine theta for tangent theta. So my last step here is tangent theta is sine theta over cosine theta, and that is indeed equal to sine theta over cosine theta. So since I ended up with a true statement at the very end, those are definitely equal, then I have proven that tangent theta equals sine theta times secant theta, because I ended up with that pink statement at the bottom. So that's kind of the goal. That's kind of where you're going with these. These are going to get harder as we learn more, but as long as you have your identities handy and you have them either memorized or right beside you, depending on what's allowed, you're going to be able to do this. It's not very hard. We have 2 more identities here, or sorry, we have a theorem, Pythagorean theorem, and then the Pythagorean identity. So the Pythagorean theorem, you're probably familiar with, a squared plus b squared equals c squared. And then we extended that to the Pythagorean identity, where sine squared plus cosine squared theta, sine squared theta plus cosine squared theta equals 1. And we've kind of explored that in previous videos. I'm not going to go into that right now, but we're going to use that identity to solve this problem. Given that sine theta equals negative square root 6/5, and theta is in the fourth quadrant, that is important, find secant theta. So if we're wanting to find secant theta, its reciprocal identity is cosine theta. And I've got some things up here that can help me get there. I can use the second identity because if I find cosine, then I can use cosine to find secant because they're reciprocal identity or reciprocal functions. So I'm going to write out my identity sine squared theta plus cosine squared theta equals 1. It's always a good idea that if you're going to use a formula or an identity that you go ahead and write it out first. And then once you get used to writing it out over and over and over again, now it's in your mind. All right, I know that sine theta is negative square root 6/5, but I'm squaring it. I don't know cosine squared theta, and then 1. So now I have a simple algebra problem, and I can just solve for cosine. If I square negative root 6/5, I'm going to have to continue up here. Sorry, guys, I should have given myself more room. Negative square root 6 squared is positive 6, and then 5 squared is 25. Plus cosine squared theta equals 1. Then I'm going to subtract 6/25. I'm going to change 1 to 25/25 just to get that common denominator. You don't have to do that. If you are doing it by hand, you do. But if you're using a calculator, you can do 1 minus 6/25. And then I'm going to do math, fraction, enter. And I want to keep it in fraction form because you want to do these in exact answers. 19/25. Okay, and then the last step, since it's squared, I'm going to square root both sides to undo the squared. Whenever we're doing this, whenever you square root both sides, we have to take into consideration the positive, negative, but this is the point where we need to figure out if we're looking for the positive or the negative solution. Now, earlier it said that it's in the fourth quadrant. So I'm going to draw a little coordinate plane here. This is 1, 2, 3, 4. So it's in this quadrant. And if you remember our memory device, all students take calculus, or awesome students take calculus, whatever, not all students do. But basically that was showing where those functions are positive. So all functions are positive here, sine functions positive here, tangent functions, and then cosine functions, which means that if we're in the fourth quadrant, then cosine is positive. So I only need to consider the positive square root answer. I'm going to continue again. Sorry about the lack of space here. I'm going to continue up here. Cosine theta equals the positive square root of 19/25. I can simplify that. Square root of 19 over square root of 25, which is 5. But I'm not done. This was asking for secant theta. So I found cosine theta. How can I use that to find secant theta? I'm going to have to use my reciprocal identity. Secant theta is 1 over cosine. So we're going to flip that fraction to get secant. It's the reciprocal. But we don't like the square root in the bottom. We're going to rationalize this fraction, rationalize the denominator by multiplying by what's in the denominator. And we get 5 square root 19/19. And that is the solution. It is positive because it's a cosine function and is in the fourth quadrant, so we're good there. That's all at once. Okay, next one. We're going to prove 1 plus tangent squared theta equals secant squared theta using the Pythagorean identity. So I want you to first try this on your own. So I want you to pause it, try it on your own, and then come back and check and see if you can get it. This one's going to be a little bit more involved than our first example, but I think with the identities above, you can do it. So pause it, try it, come back and check. There are really several ways you can approach this problem. If you find yourself going in circles where you just end up where you started, then reattack, just try something else. I did go ahead and convert both of those functions because I felt like with the cosine squared in the bottom, that might be easier to deal with on both of those fractions. In the previous example, the very first example, I just dealt with one side and that worked. But with this one, I wanted to go ahead and convert both. If you didn't do that and you got a true statement, you proved it, then that's fine. And then from here, there's again, two ways you can approach this problem. I could subtract this over here since I have a common denominator there, and then use some Pythagorean identities to simplify, or I could convert this to have a common denominator with this and go from there. So if you did one over the other, that's fine. I'm going to go ahead and maybe take what might be considered the harder route, because why not? I'm going to change this 1 to have a denominator of cosine squared so that I can add these two fractions here on the left. Now on the left side, I have a common denominator. So I'm going to add the numerators. And then I have one common denominator. I can do several things here. I'm seeing a lot of things I can do. So my brain's kind of spinning. This is a Pythagorean identity. Sine squared theta plus cosine squared theta, or flip that, is 1. And then I have 1 over cosine squared equals 1 over cosine squared, which is true. I could take a harder route and I could multiply both sides by cosine squared theta, and that would eliminate the denominators. And then I would have cosine squared theta plus sine squared theta equals 1, which is, again, true. So there's just a lot of ways to approach this. So it's not necessarily a wrong way. There might be a more difficult way, but it's still not wrong. I'm going to go ahead and change this by the Pythagorean identity to 1 over cosine squared theta equals 1 over cosine squared theta. Those are equal, so I could be considered finished. It's proven. I could take it one step further and I could say, well, that's secant squared theta, and that's secant squared theta. And that's true. So either of those are okay. I feel like this kind of tidies it up a little bit more, but obviously these are equal, so you would be done there. And then the other case where if you had multiplied by cosine squared theta on both sides, you would end up with 1 equals 1, which again, true statement. So we have indeed proved this. That's done. Well, since that's true, then this is considered proven. Now that we've proven this, this is something that we can use later on in problems to help solve harder problems. So we're proving these identities so that we can say, without a doubt, these are true. And now we can use them later on to solve problems. Anyway, so that's kind of cool. I think that's awesome. All right, we have this example. Verify sine squared theta plus cosine squared theta equals 1 using these sides, 5, 12, 13 of a right triangle in the first quadrant. And remember, in the first quadrant, all functions are positive. So I don't have to worry about a negative solution here. It does help with problems like this to go ahead and draw a picture. It said it's in the first quadrant. So this is going to be my triangle here. And we've got 5, 12, and 13. So I know 13 is going to be the hypotenuse. And then I'm going to put 5 here and 12 here. And then this is going to be considered theta. So if we're talking about sine, if we use SOHCAHTOA, sine is opposite over hypotenuse. And then I'm doing squared because I have sine squared. Cosine is adjacent over hypotenuse. Squared, because it's cosine squared, equals 1. Now, if I had chosen to put 12 here and 5 here, that would have been okay in this case because I would have gotten 12 over 13 squared and 5 over 13 squared. So it's same. So that doesn't really matter if you had chosen to put that in a different place for this problem. And then I'm just going to simplify to verify this identity. 5 squared is 25, 13 squared is 169, 12 squared is 144, 13 squared is 169. And then I do have a common denominator, so I can add my numerators. And 169 divided by 169 is, in fact, 1. I end up with a true statement. So I have proven that sine squared theta plus cosine squared theta equals 1 using those sides. That's all at once. Okay, moving on to some different stuff. I have a table here kind of listing out some more identities and just identities. So we have even and odd identities. Recall from algebra that if f of negative x equals x, then the function was even. For example, x squared. It's an even function. The 2 is an even number. The end behavior, they both point up or down depending on the coefficient. When you plug in negative x and you square it, you get positive x, even function. That was a lot, but bear with me. And then if f of negative x equals negative x, then the function was odd. An example of that was x to the third. So if you plug in negative x to x to the third, you end up with negative x to the third, odd function. 3 is odd. There you go. So down here, I have some identities that you will probably need to put on that note card or that piece of paper if you have it running of examples of even and odd functions. So even functions, cosine of negative x is cosine x, and secant of negative x is secant x. So those are even. And then your odd functions are sine, tangent, cosecant, cotangent. Really, all you need to remember here is that sine and tangent, and then their reciprocal functions. And then cosine and its reciprocal function. So it looks like a lot to remember, but it's really not. And then we have some co-function identities here that we can also use to help us on the examples below. Sine theta equals cosine pi over 2 minus theta. This is basically like complementary angles. So the sine of an angle is equal to the cosine of the complementary angle, since pi over 2 is 90. If I'm losing you there, don't worry about it. These are the identities. We will use them in a second, and you'll start to see where they come into play. All right, here we go. If cosine pi over 2 minus x equals 4/5, then find sine of negative x. So they're giving us this here is 4/5. Then we can find sine of theta. And if we know sine of theta, then we can find sine of negative theta, or negative x in this case. It sounds harder than it is, but it's very straightforward, I promise you. So from the table above, I know that cosine of pi over 2 minus x is actually sine x in this case. I could have used theta, but I went with x. So sine of x, those are equal. So I can say sine x is 4/5. I also know that sine of negative x is equal to negative sine x. So I'm going to substitute that, negative sine x. But I stated on the left side that sine x is 4/5. Bring down the negative. And that's all at once. So your answer is negative 4/5. That's it. So you can see how having those identities handy is definitely helpful. All right, next one, actually the last one on this lesson, secant x times cosine pi over 2 minus x. We're going to simplify that. We know that from the previous example and from the table that this equals sine x. We also know from our reciprocal identities that secant x is the same as 1 over cosine x. So what I really have is 1 over cosine x times sine x. If I do a little bit of simplifying here, and I multiply these components, I end up with sine x over cosine x, which is what? Tangent x. Look at all those identities we used. All right, that's all for this lesson. I hope I gave you some tools that will be helpful as you prove stuff and solve problems. If you have any questions, please let me know. I'd be happy to help, and I'll see you in the next one.